Okay, hi everyone. Welcome to Tachyon's Python 3.15 sample portfolios is faster than your code. Today we are joined by two people helping moving the Python performance faster. Pablo Galindo is C Python course developers, also the Python 3.10's 3.11's release managers. And Laszlo is the Python 3.15 new portfolios infrastructures contributors. And please join me in welcome the Pablo's and Laszlo's talk.
Thank you, man. All right. Welcome to this session on Pablo makes another profiler for the fourth year in a row. All different. Cool. So I'm Pablo. I work for HRT.
I'm Laszlo, and I work at Bloomberg.
And we are here to beat the record of how many words can a human being say in 15 minutes. All right, so cool. We wanted to chat you, to talk to you about Tachyon, which is a sampling profiler that is going to ship in Python 3.15. So Tachyon is full of features and it's really amazing, and it's just impossible to just squeeze everything in 15 minutes. So I'm willing to still try it. But the idea is that I wanted to tell you why we are making this thing and show you a bunch of the cooler optimizations that we are doing. And then Laszlo later is going to show you how can you use it and a bunch of the things that you can use with Tachyon. But I suppose for that we need to start basically saying what is a sampling profiler, right? So what is this thing even? So, the standard library sits with a profiler, it's called cprofile, and the difference is that cprofile lives in your program, and it kind of as your program is going, it traces through your program. Unfortunately, this makes your program very slow, which kind of defeats the point, but hey, I'm just an employee. Whoops. So the cool thing about a sampling profile is that instead of living in your program, it's another program that kind of picks, it reaches through the void, it grabs some bytes from the other program and reinterprets those bytes. And the cool idea of this is that the program that you are inspecting runs at full speed. And this makes it really cool because you can have your program running at full production speed, and then you can just read from the other one and get all the information that you need. Of course, it cannot see every single system, call that will happen, but it will use the power of math just to know, and statistics to know what's going on. So an example of this, this thing over here will be your Python program, and every block in the darkest shade will be a different frame. So this will be a function, and then if this function calls another function, then you put another frame in the stack. So at some point you will have your profiler on the other side. And what will happen is that as your program is running, from time to time your profiler will pick into the other one, and then it will copy all the frames, right? So here we see that there is these three calls, and you can imagine that then the profiler writes to disk. But then the program keeps evolving, and in this case the profiler cannot even see this because it only samples many times a second. So in this case, this call is unregistered, and then the program calls another thing, and then the profiler picks and copies the memory, right? So you are not seeing everything, but the idea is that if you sample fast enough, and if your program is regular enough, or you sample for enough time, and then using the power of statistics, you basically will have a very good idea of what your program is doing. All of this is done using this mega hacker, ultra complicated system calls called process VM read B. And this is very cool. It will allow you to just reach into the memory space of a different program and just grab raw bytes. And this is very important because, as you will see in a second, these profilers don't grab objects or pickles or whatever. It just copy bytes. And then what makes these things very difficult is that they need to reinterpret those bytes into the object they represent. So why doing this, right? Because you can say, hey, Pablo, there is a bazillion other profilers, so why yours is better? Good question. So first, the thing is that these profilers have this very difficult job of copying these objects and reinterpret things, and they do this thing. This is not legal, right? The Python interpreter doesn't have APIs for this. They need to literally copy the bytes and reconstruct every single time how things work. And the problem is that Python doesn't care about this thing before 3.15. So Python keep breaking the profilers on every release, and not only that, it makes their life harder and harder in such ways sometimes that it makes it really, really slow. So for instance, profiler 3.13 was slightly slower than profiler 3.12, just because Python changed in a way that it was much harder for the profilers to keep up, right? So first, we wanted to have a canonical profiler, so other profilers can kind of ensure that we are not going to break them. And also, unfortunately, these profilers, precisely for this reason, take a lot to support new versions. So when Python 3.14 was released, all these profilers took months to catch up. And also, in the standard library, we don't have profilers. We also like profilers. We are humans, after all. So, so having a good profiler for the standard library allows us to profile Python as it's developed. So that's a bunch of ideas that we have. So precisely in this topic of like ensuring that we don't break profilers, secretly and unbeknownst to everyone, in Python 3.12, I added this secret task here that implemented a mini profiler. Haha, you didn't know that, huh? So with this, there is this underscore test external inspection, and then you can pass a PID, and it will tell you like the stack trace of the other process. And this was just a test to ensure that we didn't break profilers. It was not a real profile, it's just one sample. It's just ensuring that the thing worked. But then Pep, I always say this wrong, I say 6, 7, 8, but like no, it's 7, 6, 8. So then Pep 6, 7, 8 appear, and this is totally different. Yeah, it's kind of hard not to fall into it. So this is a different thing that we did with Matt and Ivona. So this was a way to basically allow external debuggers to attach. It's not the same thing, but it gave us another piece of the puzzle that will allow what Tachyon is. So this allows the interpreter to basically expose its information in such a way that debuggers could understand, but profilers could do as well. And this led us to PyCon US 2025, which was a wild PyCon when I wear all different ways of hats and costumes and all forms of humiliation. And at the end, of the conference in the sprints, I approached Laszlo and I say, "Hey man, wouldn't it be cool to just call this thing in a loop?" And then just like, call pickle or something. And then it's a profiler. And theoretically it is, right? And then we said, okay, we have this profiler. How fast is this going to be? Is it going to be like 1 million times a second? No, it was 4 times a second. And this makes it the slowest profiler on the planet. And then, so yeah, that's not great. But then during the sprints, we spent like all the sprints adding optimizations and making things that were stupid, not stupid. And then after that, as of today, this is the fastest profiler of Python that is released publicly. Asterisk, you will see that at the end. But as you will see, I wanted to show you here some of the optimizations that are unique of this profiler. And the reasons we could do these optimizations is not because we are smarter, it's because we also control CPython. Secret trick. The developer used this weird trick to win all profilers. All right, so let me show you some of the coolest tricks. So this is not all the reasons this is very fast, but it's some of the coolest one. All right, so let's go with that. So first, every read that the profiler does is a syscall. So a syscall by in average takes between 1 and 5 microseconds. So the moment you need to do a lot of reads, it makes your profiler slower. So the idea is do as little reads as possible. So how many reads do we need to do? So first, the profiler needs to go to this mega god crazy structure that we have in the interpreter called PyRuntime. PyRuntime holds a linked list, your favorite data structure. So if you do interviews and you were saying, where are the linked lists? They are here. So, so the runtime has a bunch of interpreters, and the linked list is this very stupid data structure because you cannot copy all of them in one go. You need to copy one, and then you have the pointer, and then you copy the other thing. Very fun. And then every interpreter will have another linked list of threads, and then guess what the threads have? Oh yes, another linked list of frames. And that's the end, right? But then every frame has a call object, so there's more things, right? So you will have a call object, and then the call object will have 3 pointers to a string. So like every time you see an arrow, here is a copy. So if you think about this, every sample, if you have like a program with 2 threads and perhaps like 300 frames, that's like 2 times 3 times like 4 times the number of call objects. So it's a lot of copies, right? So that's bad. So the idea is that we want to start to simplify this, so we reduce the number of copies. The first thing we realize is that call objects are more or less the same, right? Like they don't change. Like the name of the function doesn't change across hopefully, unless you do weird shit. But like the name of the function won't change across the lifetime of the program, and the file names won't change. So ideally, this is something that we can try to cache. So you can imagine that instead of copying call objects, you will have a cache, and they will say, hey, here's an address of a call object, give me the call object, and then if I have it in the cache, I just use it. Otherwise, you actually do the copy. Unfortunately, this doesn't work. The reason it doesn't work is that call objects can get destroyed and new call objects can get created, and they use the same address. In particular, you can do this with lambdas. So if you create a lambda and then you destroy the lambda and then you create another lambda, the address of the call object can be reused. So you cannot just assume that. So we have this secret code that nobody knows about. So every time you destroy that call object, we bump a number. So that's the generation. And what we do is that when you cache all the call objects, and then you remember the generations that those call objects had. So if a single call object is deallocated, we we destroy the entire cache. But because hopefully this happens very rarely, fingers crossed, then we can reuse the cache quite a lot. And in practice, this is true, right? So this is a way that making the interpreter know a bit more about these generation things. We can ensure that we can cache call objects, and this allows us to remove at least 4 copies per frame. So that's very cool. The other thing that we do, so instead of like caching per address, we cache per generation. So the other thing that we do is that when we make a copy, normally memory is represented in pages. So all the primitives in Linux and other OSs work at the level of pages, not at the level of bytes. So when you copy like a byte in a page, you say, I want just these 3 bytes from this address, the kernel really needs to like lock the entire page, and most of the overhead is that locking. So what we do instead is that instead of copying those 5 bytes, we copy the entire page over, and if you want to copy little things across that memory address, we already have the memory in, and this amortizes like the cost. And copying the page is more or less the same copy as copy the bytes, so that makes copying many things that are close together in memory really fast. And the other cool trick that we have is that if you think about it, copying the linked list of frames is just not possible to avoid, because you will have the frames, and the frames are linked in the linked list, so you need one of these system calls per frame. So you have 100 frames, you need to do 100 of these, and that's very bad. But in Python 3.12, Mark Shannon added this very cool thing in which like the memory that is back in the frames, so not the frames themselves, but the memory that is back in the frames is actually like close together. So basically it looks a bit like this. So instead of having, you will have the linked list of frames, but the memory that is inside the frames are in these kind of like chunks that are also in another linked list, because why not? And it's all linked lists. And the idea here is that instead of copying the frames, you will copy those chunks. So in these particular examples, if you think about it, you will copy first the first chunk, you will copy the second one, and then you will copy the third one. But those chunks contain all the memory of all the frames underneath. So in this particular example, for only 3 copies, I copy 4 frames. In reality, this number is much bigger. It's like probably 2 copies gives you like hundreds of frames. So this allows you hundreds of copies less, just for the copy of the chunks. This literally is one of the optimizations that saves most of the time. The other thing, so instead of like, one system call per frame, you have one system call per chunk. And then the other thing that we did is a very cool idea that we call it a frame cache. And this is a bit complicated, so let's see if I can explain it correctly. So if you think about it, when the profiler, so the profiler is on the right, the program is on the left. So let's say we have a bunch of frames. So here this program is calling D, and then C, B, and A. So A is the bottom frame. So in this particular case, let's say the profiler copies the frames over. So most of the time, this profiler is so fast that the next sample that it takes, Python has not done anything different on Python land. Like it's executing C, or you can imagine that it's executing some pandas code, or so like NumPy or whatever. And then the Python stack is the same. So the next time the profiler copies these frames over, it's going to be the same frames. But you don't know that, so you need to copy all of the frames anyway, right? And that's kind of like annoying. Not only that, you can imagine that most of the time what your program will do is that it will call a bunch of functions, and it will only change the functions at the bottom. But you need to still copy all of them because you don't know if the first frame is going to change. So that's kind of annoying. So in this particular case, if the function doesn't change, we need to copy it over, and that's bad. So the optimization we did is that what we're going to do is that when you copy a bunch of frames, so all of these frames, we're going to keep them in memory. So apart from recording to this, we're going to keep them in memory. And then we're going to use the evil twin of process VM readB, which is process VM writeB, which is the salsa version, like that. That's when the danger is. And this version allows us to write to the process. So the process has a secret new place, which is like a new kind of a slot that we call last profile frame, which here I'm going to call last frame in a second. So what happens is the following. We copy the frames, and then we cache them. And then we have this kind of pointer that is both in the profiler and the process being profiled. And this pointer will point to the latest frame that we copy. In this case, it's A, right? So because we copy A, B, C, A, B, C, and D. So we have A, B, C, and D. And the last one that we saw in the top is A. So we set to A. So what will happen is that the next time we are going to make a sample, we just copy that pointer over there, and then we say that it's still A. That means that the frames have not changed, so we don't copy anything. And then you can say, well, what happens if the frames actually change? So the interpreter is made in such a way that if the frames change, so for example, let's say A returns, so now we're in B, and then B returns, so we're in C. So the interpreter is made in such a way that when you return, the number on the process side changes to the parent, and only to the parent. It never changes back if you call functions. It only changes when you return from the functions. So right now, let's say we make another copy, we compare these two, and then we say that, oh, it's not A, so we cannot use the frames that we copy, but we see that it's C, and we have C and D, so we still don't copy. We just throw away some of those frames. So as you can see, most of the time, we can get away with samples with 0 copies. And amortized, this makes us able to sample faster than the theoretical limit of the system call. Because again, if a system call is 1 microsecond, the theoretical limit will be 1 megahertz. But because most of the time we don't need to copy, well, I mean, just that one, but we can achieve this in like even more than 1 megahertz, which is like 1 million times. So if the function, of course, like call more functions, you need to copy the new frames. But when you find that you have a frame in the cache, you reuse the cache. So like this is really, really, really efficient. Cool. So now, after this extremely fast talk, Laszlo is going to tell you about how to actually use this super cool thing.
All right. I'm sure. I'm sure all that made perfect sense. Everyone understands really well now how Tachyon works. So maybe we slow down a little bit, look at some pretty pictures. And we're going to take a look at how Tachyon works. Now, Tachyon is not one of these features which is now just being introduced and it's going to get more and more features and it's going to be built up over time. No, this is actually a really complete profiler. It has a lot of features. And I would not have time to cover all of those for sure, not even if I go at Pablo's speed, which I cannot. So we are only going to look at sort of the basics and give you some highlights about how it works and how we can get started with it. So this is how you can run it. It's pretty simple. The profiling package you see here is a new thing in CPython 3.15, and the intention with this is that now this groups all of the all of the profilers in one package. This also means that cprofile now also is hosted here, so you can find it under the tracing name. So you don't have to keep remembering whether the C or the P is capital or whatever. It's all in one place. Now, the first thing you have to decide when you're trying to use Tachyon is what capture mode you're going to use. The capture modes it supports are run, when you basically just take a script or a module and then you run that through Tachyon. You can also attach to an already running process, or you can take sort of a quick dump of an existing process and see what's going on there, or you can replay a previously captured sample. We're going to take a look at that later. When you use run, you specify a script or a module, and in that case, Tachyon is going to start a subprocess and invoke your script in that subprocess. And the sampling process is going to start as soon as the interpreter is initialized, which means that all of the samples taken are going to, you're going to get samples from the very beginning, all the way up to the duration you specified or to the end of the script. Now with attach, you can attach to an already running process. So you specify the process ID, and in this case, Tachyon is being invoked remotely, so that it attaches it to that Python interpreter, and you're going to get sampling data from that point onwards. With dump, again, Tachyon attaches to that process. You specify the process ID, but in this case, Tachyon just runs a single sort of snapshot of the memory, all of the frames. It dumps it out, and then it exits, and you get basically a snapshot of what's going on in that process. Now let's talk about reporters. Not these kind of reporters. These ones. So once you have sampling data collected, you also need to visualize that. You need to do something with that data, so basically you can make decisions and understand what exactly is going on. Tachyon supports multiple different sampling visualizations, and in order to decide which one's best for whatever use case, we're going to look at a couple of questions and see what would be the best one for each of these. Now, when you're just getting started and you want to take a look quickly at how your program is performing, the simplest thing to do is to start with pstats. Pstats is an existing format which has existed in CPython, and this is the default in Tachyon as well. So when you run Tachyon, that's the default, you don't have to specify it, and this gives you basically a terminal sort of output in the shell, where you see some basic information about the sampling process and all of the process or all of the functions ordered by samples or whatever, however you configure it, basically whatever is taking the most amount of time or the most samples. You also get some insights at the bottom there. pstats is also, because it's an existing format, you can write it as a file, and you can, because CPython already has an API around that, you can use all of the existing tooling and the API around that file as well. Now, a completely different situation. Let's say it's 2 a.m. in the morning and you're being paged and then the servers are on fire and you need to figure out why this Python process is super slow. Now, if you happen to be running CPython 3.15, which you're probably not doing because it's still in beta, but if you were doing that, you could use --live, and with that, Tachyon can attach to the running process. And because it's really low overhead, as Pablo explained, this works perfectly fine with the production application. It should not affect that too much. And when you do this, you're going to get a view like this on the terminal. This is a top-like view showing you what's going on in the process currently, ordered by, well, there are various different sorting modes where you can see basically what's taking up the most amount of time in that process currently. You also get a lot of details, what's going on with sort of the GIL and how the sampling is working, and there are many, many other options here. So this should give you a really easy way to pin down what may be going on, what may be the culprit performance issues. If you want to get a more holistic view of your application, what paths might be leading to sort of slowness in that program, then the flame graph is a really good output mode. A flame graph is a visual representation of your program where you can see each stack frame as a cell here, or a rectangle. The width of that rectangle shows you how many samples have been collected, and also the color coding shows you that. So here, for example, as you're going from the top, the entry point, which is obviously running, it appears in all of the samples during the duration of the program. You keep going down, you will see that this public API request is what's taking most amount of time in this application, and all of the calls inside that basically doing different things. Now, the flame graph reporter Tachyon ships is a dynamic reporter. It gives you a single HTML file with all of the JavaScript and CSS bundled, so you don't need network connections for that. And it gives you a really nice and easy way to sort of dig in. You can zoom in into the frames. You get this nice tooltip giving you information where you can, for example, see that the business logic here called burn is actually doing a lot of square root calculations. So someone should optimize that probably. There's a lot of features here. For example, you can search. You can invert the flame graph. It also has dark mode, yes, it's also there. And then many, many more cool things. Now, if your focus is basically on optimizing a file or maybe a function, and that's basically your scope, and that's where you want to focus, then the heat map is a really good visualization type. The heat map gives you a HTML output with your source code interleaved with a visual representation of the intensity of the code on each of these lines. So it gives you a really easy way to spot where you might want to spend time on optimizing performance. You can see those arrows on the right-hand side that lets you go up and down in the stack frame, so you can figure out where the calls are coming from and what things are being called from those locations. And this also, we can also look at a really cool trick Tachyon can do. If you enable opcode profiling, then you will also see, you can see that red rectangle there, you will see the opcodes, the CPython is actually, the bytecodes CPython is invoking, and it even shows you if the specialized adaptive interpreter specializes those instructions, you will also see those there, which can be super useful, I guess, especially if you're a core developer and you want to look at these details. This is also available on multiple other output types. Now, if you're looking at making some changes in a program, and maybe you're curious whether you improve the performance or maybe you introduce the regression in performance, then you can look at the differential flame graph output. What this gives you is a very similar view to the flame graph visualization, but the color coding is different. When you see gray, that means that the performance is within a 15% difference, so probably very similar. And blue cells show you shades of blue, performance improvement, and shades of red show you performance degradation. And you also get in the tooltip, you will see a bunch of information about what exactly is the difference and what's going on. And again, the square root is there. Yeah, someone should do something about that. Now, if you have a very particular need or desire to use the Firefox Profiler Visualizer, then we've got you covered as well. With --gecko, you can produce this JSON file format, which you can load into the Firefox Profile Visualizer. This is a really cool tool, which I think was designed for JavaScript, but it works really well with the sampling data Tachyon emits. And here you can also see another cool trick, which is that even though this was not designed for Python at all, with this visualization, Tachyon can emit data which shows you really cool and interesting information about Python. For example, when is native or when is Python code being executed, what's the GIL, who's holding the GIL, whether the GC is collecting. And you can also see the opcodes here, the bytecodes being invoked. Now, if you want to maybe run a sampling process and you want to look at various different output types and you don't want to rerun the same sampling to get different visualizations, you can also use dash binary. In this mode, Tachyon will save a single binary file. In a very efficient representation, it saves the sampling data, and then it lets you replay that into all of the different visualization types Tachyon supports. In this way, you would first do a run, dash binary, and save that data. And then you can call replay as many times as you want and produce all the different visualization types from the same sampling data. Now, this is just sort of scratching the surface. Tachyon has a lot more to offer and a lot of cool features. I highly recommend checking out the documentation, which is very extensive and has all of these details. And yeah, that's really Tachyon. I think with all this, Pablo, I guess you're done now, right? You're done building profilers.
That's a perfect segue to my new section, which is that, no, I have more profilers. So Tachyon is really cool, and we think it's the best profiler as of today for Python. But Tachyon has one particular limitation, which is that it lives in the standard library, and my fellow core developers will hate me if I put a nuclear power plant of a profiler in the standard library. So it only profiles Python. Very fast, but only Python. And as you know, Python has a lot of other things normally running underneath, right? Like you run pandas, polars, NumPy, TensorFlow, Torch, whatever. So normally, if that happens under a function called, calculate, then it's not very useful that you're spending 90% of your time in calculate. So that's unfortunate. Unfortunately, Tachyon will never learn how to profile those parts because, CPython as of today at least is written in C, the legal language. Implementing all those features in C is really, really hard and really verbose and really complex. So at my employer HRT, I have been developing Tachyon's big brother, which is called Chronon. I'm very good with names. Anyway, so Chronon can do everything that Tachyon can do and much, much more. It can just sample also like native frames, and it has a bunch of features that are really useful when you deploy this at the scale. Like for instance, it has the possibility of taking snapshots as the profile is going. It has a Python API. You can use it as a control plane. It also supports analysis of core files, and you can dump as well as Tachyon does, but also with the native frames and many, many other forms of support. It also supports the streaming mode. It supports creating files as it goes, so it doesn't blow up the memory. It supports really long streaming sections. And right now we are using it very successfully at HRT. We have replaced every use of, or almost every use of the previous profilers. And the good news is that we plan to open source it at some point this year, hopefully in the next quarters. And we are sure that you will love it. So with this, I think it concludes our cool presentation. So we have some time for questions, I think 3 minutes. So thank you very much.
Hello, thank you. So I'm a maintainer of Django, and I was wondering if we could use Tachyon in a way where we attach it to our test suite run so we can detect when performance degrades.
Oh yeah, totally. And actually, one of the things that we didn't discuss because we didn't have time is that Tachyon supports a sync.io mode. So normally in a sync.io, the caller will be the even loop. So you will see select, and that's not very useful. So with Tachyon, you can see all tasks that are running or all tasks that exist whatsoever. So if you have a task that is just waiting for like a 6 gigabyte file, you will see that most of the time you're waiting for that as well. So you use Django async like that is possible.
Thank you.
Very cool.
With C profile, the problem was with decorators, you could not realize what the function you were decorating was because it operated on the code, like the CO variables. Does Tachyon handle that? Like, does it use the __ name of a function when it reports the data?
It uses qual name. So it shows you like the fully qualified name. It's something that we added, I think, in Python 3.13, no, 3.12. So it tells you like, if for instance a method in a class, it will show you class.method. But if you decorate and you don't change the qual name, it will show you whatever it was before.
Okay, thank you.
Thank you for the talk. Do we have a special sampling method for multi-threading? Because if you start a process that's single-threaded, then it just bumps into 20, 30, 50 threads, the same sampling mechanism would be like not exactly a good fit?
Excellent question. Actually, that leads us to something that we have not touched with, is that a lot of people say, like, why you need 1,000,000 times a second? You know? So that sounds illegal. So the idea is that if you have many threads, that is divided by the number of threads. So you have like 10 threads, Tachyon will sample every thread. So if you have 1,000,000 threads, hopefully not, then you will sample at 1 sample per second. So you know that is very important, not only to be fast for a single thread, but also because you can have many threads. In this particular case, so Tachyon doesn't care about the number of threads. It will still weight correctly the samples in different threads independently, and all reporters that support different threads will have the information separately. It also supports processes, so you have processes, it will do the same thing, except that in that case, Tachyon will fork itself, and it will spawn a version of itself per process. So in that way, you can have thousands of processes if you want, and that's fine. It's just that it will produce one file per process, and also supports free threading. So if you have multiple threads, Tachyon will run multiple threads with Tachyon per thread unbounded, so like you can just have full profiling with no overhead.
Thank you.
Thank you for the talk. To profile a process, does it have to be the same Python version of the profiling process? And specifically, can you profile processes with Python versions before 3.15?
No, but Chronon can.
How much is it?
$9.99.
Is it able to merge if you have like a process pool that forks and then merge back the reports?
No, but Chronon can.
I see a pattern here.
Whoopsie.
Is PySpy and Austin going to die?
I don't think so. I mean, the idea, as I mentioned at the beginning, that's very dramatic. Like, no, but Chronon can. But like, I mean, the idea is that at least this also shares. Ideally, this will make PySpy maintainers' life easier as well if they want to not die. That's up to them. But like the idea here is that first, the same tricks that, like, nothing is secret here, right? Like you can read the code and you can re-implement this thing in Rust, the language of the gods or whatever, and then it will be even faster because obviously the core of Tachyon is C, but all the reporter side is Python. So of course we cannot go as fast as theoretically we could because like there is a lot of Python code, and you know Python perhaps is not super fast. Maybe we should Tachyon, like, you know, which you can do. You can also Chronon, it's very cool. Because, yeah. So in that case, no. And actually, ideally, for instance, if they want to support 3.15, they can check all the things that Tachyon does, and then they can just implement that thing. And also, all the mechanisms that we are adding, they can use as well. So they can profile even much faster if they want. And they can use all the techniques that we use as well. For instance, the PEP 678.
7.6.
Okay, yeah, so they can do it as well. So no profiler needs to die, and actually it's much better that they don't die. Like most of these techniques some of the techniques that I have not talked here are techniques that those profilers use as well, and they have discovered over the years. So having multiple profilers is actually a good idea because it gives a very rich ecosystem, and like some profilers are better than others for different things. So that is good, right? That just more than one person is doing. Here, we wanted one in the standard library that works really well, that is shipped with Python and always works, and we wanted to ensure that we don't break suddenly the profiling world.
Thank you.
Thank you both for the great talk. I'm wondering, for Chrono, does it mean that it will not be able to sample at the same rate because you have to deal with native stacks and maybe deal with dwarf files if there's no frame pointers and things like that?
Yeah, so Chrono, I implemented a full dwarf parser and a full dwarf unwinder that is really, really fast. Like what it does is that it doesn't stop the thread. Like what happens when you sample native threads is that you need to stop the thread for a long time while you do the unwinding. This was a new technique called asynchronous unwinding, which just like gets the registers a bit of the stack and winds asynchronously. But of course, like that is an extra cost, as you mean, and also we need to merge the frames, so that's another operation. And indeed, it cannot achieve 1 million frames per second, but it can achieve 200,000, which is insane.
Thank you.
All right. Thank you very much.
All right, thank you.
That's it.